Hello everybody. I am aware of my accent, so I apologize for that. Every time you cringe, remember I cringe with you. My name is Eugene Panferov. It tells you nothing, so we can focus on the topic of this presentation, which is the proposal of a data language. A pretty rare thing nowadays. How many new data languages have you met for the recent 30 years? Edgar Code in 1972 stated his anticipation as follows. He expected in his near future a great variety of languages to be proposed for interrogating databases. 40 years passed. Where are they? He didn't think that SQL is the final solution for the problem. He considered his own child SQL to be a provocation for development. But it never happened. We decided that SQL is the final solution. And we developed the Great Divide, which I blame for this stagnation. Because it sounds good that we divide our problem into two sub-problems, algorithm representation and data representation. And we achieved quite a lot on the left side. I'm not satisfied with this development, but at least there is some development. And on the right side, on the data side, we basically reverted back to no formalism. From a single unsatisfactory formalism for 40 years of stagnation and development, we reverted back to everything maintained manually, no formalism at all. That's the state of affairs. The problem is that this great divide is nonsensical. We can speak about two sub-problems of algorithm representation and data representation separately. But in reality, we cannot solve these problems separately, because software is data manipulation. It is data manipulation and nothing more. So for the last 40 years, we were developing a single-sided coin. So my ultimate goal is to stop this nonsense and integrate an advanced data language into a general purpose language. Make it possible to speak about data in a general purpose language as a native part of this language. And I insist to use a relational data model for that, not because of the SQL, but because the power of the relational model. Relational model seems to be all-encompassing. You can represent any knowledge, any possible knowledge in the world, you can represent as the hierarchy of relations. And you are doing it every day as you speak about anything, literally anything. If something is speakable of, by speaking about it, you are automatically building a hierarchy of relations. This graph in particular on this slide doesn't represent anything, but it doesn't represent anything particular except the possibility of an arbitrarily complex configuration of relations. But it took me 10 seconds maybe to scribe inside this perfectly random graph an abstract example. A man writes a book hastily. I started with a perfectly random picture. I drew it simply to show you the possibility of complex configuration, and then I scribed a concrete example into it in mere 10 seconds. And I have chosen intuitively understandable labels for the tiers of this, for the stages of this hierarchy, so that you can understand how it maps onto your language, and I hope you understand how your language maps onto the knowledge. So I choose relational model because it is powerful, all-encompassing, and complete. But SQL approach to the data, to the relational model, SQL implementation of a relational model is extremely deficient. It's highly deficient, absolutely unsatisfactory, and I'm going to explain it to you. Well, I'm sure half of you, more than half of you, already hate SQL, and you are following the cult of no SQL, I believe so. I'm about to give you perfect justification for your hate for SQL. What's the classical, by the book, SQL approach to data representation? We first draw an ER diagram. We call half of the relations entities, and half of the relations we call relations, which seems to be a violation of the relational idea right from the start. Then we map this ER diagram, classically by the book, I'm not inventing anything in this slide, into a couple of tables and a foreign key between them. All three objects represent a relation here. A table is meant to be a relation in SQL, but also a foreign key represents a relation. So right from the start we have two different representations for the same thing. And the difference is deep. The difference between this representation is the level of abstraction. Tables are fully maintained by the machine, but the machine slightly helps you to maintain foreign keys, but you need to maintain them themselves. You need to maintain them. You need to give them meaning. You need to imply meaning behind them. You invent fake type. Integer is not the type of category. So integer is already fake. You already lied to your machine about your data in this very definition. And this category ID, integer category ID, will poison, will infect all of your input and output, and you have to deal with it every day. And the foreign key is only capable of representing mere one-to-many relations. A many-to-many relation, which is more prominent in real life, is not representable with a foreign key. It takes a linked table, which is also a classical necessity of life. You cannot avoid linked tables when you are projecting your knowledge into an SQL database. And we already have three different representations for a relation: foreign keys, linked tables, and tables themselves. And these two are not variants of the same. They are fundamentally different representations. In case of foreign keys, a foreign key here on the bottom represents itself a relation. A foreign key employed with a linked table on its own does not represent a relation. So on top of the multiple dissimilar representations, we have another problem, an opposite complementary problem, that we are having two lexically and syntactically identical things in our SQL program that have absolutely opposite semantics. SQL does not maintain any visible distinctions between these two foreign keys, one of which represents a relation and another one doesn't. So problems are piling up. It's only fifth slide and we already have 4 problems. But there are more. We have inheritance. In modern databases, class inheritance is intended to represent a relation between relations. So a high order relation such as a class belongs to another class is represented by inheritance. And on top of it we have complex types, which are in fact also a representation of a higher order relations. Here's a snippet from Oracle documentation. It defines a collection, and it is lexically, it is literally indistinguishable from a definition of a table. And even in the documentation in the same chapter, they call collections nested tables. Tables represent relations. Nesting of the tables represent higher order relations, relations between relations. So that a complex type, be it a collection or array or something else, whatever you call it, it is still a representation of a relation. So we end up with a representation zoo of at least 5 different representations for the same thing, which is motivated by the impossibility of SQL to represent relations between relations. So relations between basic types called tables are perfectly representable, and everything else, relations between tables, we have to build up some other surrogate representations on top of SQL. And this piling up of different representations presents a real problem in its own, plus it creates additional problems that lead to drop of performance. Starting with the link table. Here's the link table. It represents 3 relations by creating 5 relations within a physical database. So 5 relations in terms of the database represent 3 relations in real knowledge, in the domain knowledge. 2 more unwanted relations, they are destined to decrease the performance of the database in 2 ways. Way number 1, we want to select genres of a given book, which is, you can guess, the most basic operation that you can address to this particular data scheme. You have a data scheme of books linked to genres. So your most basic operation is to select genres of a given book, and it is necessary to make a join of 3 tables. It's a triple join. The most basic operation is a triple join already. And you know joins are not cheap. Joins probably the most costly operations, well, next to sequential scans maybe, but you get the gist. But there is more. What is going, mathematically speaking, inside this triple join? Here's our problem, our initial problem. We have a relation book genre, which is by definition a subset of the Cartesian product of book and genre. So somewhere here on this 2-dimensional plane exists the entirety of our book genre relation, and we are searching for several points inside it. It's fundamentally a 2-dimensional search. And what does the join do? The join doubles our search space. by performing a Cartesian product of the book genre space with the book genre itself. A join is a Cartesian product, but in our case, in our most basic case, in our unavoidable case, it is a perfectly meaningless Cartesian product. It just doubles the search space, and instead of two-dimensional search, we do four-dimensional search. On top of that, not only with linked tables, in every case of a join is meant to create a relation, but every time the resulting relation already exists. Here, take a look at the one-to-many relation. Our very first example. Here, when we select category of an item, we join two tables by their foreign key, where foreign key represents a relation. What does it mean? It means that this join is employed to convert a representation of a relation from one representation into another representation, from yellow to white on this picture. So join merely converts representations and nothing else. But the worst part of it, it does it repetitively. You have to join this table each time you are accessing the information about the foreign key. Each time you access this highlighted in yellow relation, each time you access this yellow relation on this picture, you have to recalculate its representation, because in its original form, as it is stored in your database, it is not readable. So first, every pair of tables you ever join, you made them joinable. Your job is to make all the joins to your database perfectly predictable. You fail at making them predictable, you lose the bonus. You are a failure of a programmer. So that no join will create any new information, and it is your responsibility to make it so. So that your job as a programmer is to make joins useless, but still you have to call them every time you access information that is represented as non-tables, as foreign keys or linked tables, in order to recalculate the representation of the relation, which makes every join, a job of every join, a Sisyphus's job. Absolutely Sisyphus's job. So let's recap the flaws of SQL. Those that I just listed and some more. Costly, unnecessary joins, repetitive, useless job. Representation zoo, this mess of representations that causes all of it. Human language mimicking, inconsistent, inextensible, needlessly complicated syntax. You know it, I don't need to remind you. Mixing relational operations with the output formatting, it's more difficult, keep it in mind, and you will see what I mean when I'm going to explain my proposal. Imperative DDL, horrible thing, non-idempotent. You call create a database, not create table. Call create table twice. First time it says okay, created. Second time it throws an error. Nothing changed. Error state changed. You didn't change input, but this input produces different results. Non-idempotent DDL, horrible stuff, should be declarative. Impossibility of relations between relations, we just discussed it. And separation from the application layer language, the great divide, in which SQL itself partially responsible too. So the problem is that the major necessity of life in SQL, your core, the center of your SQL program, joins, they're useless. 90% of the work that your database is doing every day is merely conversion of the representations of relations. And your most important interest in SQL, your need for SQL, representation of relations, is not satisfied because SQL is not capable of representing higher order relations. We will discuss it in more details, but it constitutes, this impossibility constitutes our first instrumental goal. We need a language that is capable of representing higher order relations without creating a representation zoo, without creating a need for conversion of representations, different representations of relations. Here's what we have with SQL. Here's our initial hierarchy of relations that we started with. It represents some piece of real life knowledge. And when you try to translate this piece of knowledge into SQL database, first you have to choose exactly one layer of this hierarchy to be represented by means of tables. Once you have chosen it, once you have represented a single item as a table, you cannot represent relations above and below it by means of tables. You need to use something else, because tables don't nest naturally in SQL. So you employ foreign keys and link tables for higher order relations, and you have several quite useful by now mechanisms of complex types and subtypes and field constraints for representing lower level relations. Now this is the illustration of fundamental impossibility of uniform representation of everything in SQL. Apologies for this slide. For the sake of completeness, we must state our definitions. So every time referring to a relation, I mean a strictly defined mathematical relation, which is a subset of a Cartesian product of its domains. From this definition immediately follows a very obvious fact that a relation can be a domain of another relation. And SQL does not reflect this fact. When you specify a relation in terms of SQL, which is traditionally a table, you are limited to basic types. The domain of an SQL relation could only be a basic type. Such is this language. You cannot specify another table as a domain of a table. And this fact, the fact that a relation is a set and therefore can be a domain of another relation, this is specifically what makes relational database what makes relational model so powerful and so all-encompassing. Specifically because of that. Whatever you speak about, every part of speech, basically, every part of speech is a relation. And most of them, the vast majority of them, are higher order relations. In every snippet of real knowledge, most of the relations are higher order relations, so that SQL fails to satisfy the primary need of representing knowledge. What do we need to do? We need to make a language where a relation can be represented uniformly, regardless of its order. So everything on this picture should be represented uniformly, homogeneously. Transitioning to linguistic terms, we need a language that satisfies this simple closure, where domain of a relation could be a relation, highlighted here in white. And this problem immediately splits into two sub-problems. How to reflect this fact in the data storage, and how to speak in a data language that allows this fact. Because our goal of a language is to speak it. So we need speech about such complex relations. We need to make a language that makes a speech about higher order relations readable. But first, let's focus on the first part, data storage. Is it possible to map these fantasies, this philosophical lament I just expressed, is it possible to map it into concrete reality, into a physical data storage? Yes, it is possible. And this picture shows us what do we call a graph of a relation. All these yellow legs between keys of domains A and B, this is the graph of a relation. If we are able to represent this graph, we represented the relation raw. So the problem of representing arbitrary relation raw between two other arbitrary relations A and B is the problem of representing the graph of the relation raw. And this is how we solve it. As long as we index domains A and B, we can represent the graph as a finite set of integers. We can represent it as a finite set of tuples of couples of integers, but a finite set of couples of integers can always be represented as a finite set of integers. That's a mathematical fact. So a finite set of integers is always a representation of the graph of this arbitrary relation. And nothing is easier than indexing a finite set of integers. And once we build this index, we suddenly discover that we just represented an arbitrary higher order relation without invoking any mathematical miracles, without invoking new software, without invoking any breakthrough in data science. An ordinary index is capable of representing a higher order relation if we allow it to refer to more than one data node per leaf. This leaf, the leaves of this index, they refer to two data nodes each, but Is it really a complication? Once you have machinery to maintain indexes, the problem is already solved. You just need to allow an index to be a multitable index. A multitable index itself is a relation between relations. That's it. And let us reiterate this proof because it was constructive, and I hate constructive proofs, and I feel that many of you also hate constructive proofs. So make sure that these relations A and B are arbitrary relations. Throughout our proof, we did not imply any specific properties except being indexable, which is a must to have anyway. And thus we end up with a comfortable representation of a higher order relation that is already implementable right now. So you can see that the philosophical lament I started with translates into perfectly actionable idea, like more than actionable. It's almost done already. But it takes one tiny step, not in the field of software, but in the field of mental models. It takes a taboo breach and a paradigm shift. You must forget about tables. Drop them. Tables aren't relations. Indexes are relations. Indexes represent what belongs, what doesn't belong, and where is it located physically. And now we can move on to building the language. So we solved our physical problem, we solved the problem of representation. Now we are about to solve the problem of speaking. So first we must drop altogether human language mimicking. It led SQL into oblivion. I would like to maintain the separation between relational operations and data output formatting. I would like to maintain a single separator, be it the space, and drop all semicolons and commas, and drop the entire idea of something being in between, which simplifies the language dramatically. I want to make basic types and relations interchangeable. This is the key part. This is the key part. A definition of a relation is not limited to basic types accepted as the relation domains. A definition of a relation should accept other relations as domains. Simple as that. It satisfies this requirement of homogeneous, uniform representation. Variables and assignments. The language must allow and maybe focused or build around assignments. Variables, well, immutable variables. Very nice oxymoron, I know. Immutable variables. Why? Because it's a high demand. Presently in SQL, this control structure, this with clause, with is just a weird way to define assignments within SQL. They are in high demand already, so we cannot escape them, and we shouldn't try. Make data management return value. Shame on Oracle for very ugly, very shameful clause returning. Returning is a shame. It shouldn't work like that. I would like to maintain functional purity. and keep basic types as few as possible. Speaking of basic types, here's my basic types system for the proposed language. It contains 6 types, 2 of which are absolute novelty, time and time interval. I call it pragmatic typization because this type system it's not a complete system, okay? It's the basic layer of the type system. It is dictated by the capacity of these types to represent ideas in real world. The distinction between each of these 2 types presented on this slide represents some meaningful distinction in real world. The distinction between each of these 2 types does not represent a distinction of data representation in the memory of a machine. We must forget about machine memory and concentrate on the properties of knowledge that we are trying to represent. And these 6 types, they represent meaningfully distinct types that you see in real world. And forget about memory. The first class data object in our language is set of tuples. Even if it is a scalar, like even if it is a number, it is still treatable as a set of tuples. You can put a scalar in the set of tuple context and it will be treated as a set of tuple. Not necessarily the bloat memory dedicated for each scalar to be a memory dedicated to a set of tuples, but on the surface level, for a user, everything should be treatable as a set of tuples. And as we discussed above, a relational model is all-encompassing. It is capable of representing anything. And this capability stems from utilization of 2 categorically distinct categories of collections, tuples and sets. For some mathematical reason, or magic, not reason, I don't care, one is not sufficient. You cannot represent anything, any knowledge, by using only one type of collections. But if you have 2 distinct types of collections, as long as they are distinct, you are capable to represent absolutely everything. So all possible knowledge, all possible data objects of arbitrary complexity, they occur on this 2-dimensional plane, tuples and sets, if we allow for arbitrary complexity, for arbitrary nesting. On the other hand, if we add a 3rd category of collection, it will be redundant. I will show it later. So a few more boring slides. The lexic of the language. I'm trying to make it also as simple as possible. We have 7 literals, 4 pairs of brackets and 2 separators. 2 separators because we equate line breaks with spaces. 4 brackets because we have 2-dimensional plane, tuples and sets. Tuple brackets, they complicate things. They build up a tuple. Projection brackets, they dismantle a tuple. Union brackets, they build up a set. Selection brackets, they dismantle a set. 4 fundamental directions on a 2-dimensional plane. They are represented with brackets in our language. And literals are quite typical, 7 of them. We maintain distinction between capitalized and non-capitalized identifiers for no philosophical reason, but it increases readability greatly. So much it increases readability, it is worth having. For no other reason than readability. We extend number literal in Erlangish style because it's very useful, very comfortable. And we introduce a novelty, a time literal. It's a quoted literal in special quotes. It represents constants of types time and time interval. It represents a calendar date to arbitrary granularity, or time or interval between two calendar dates. Brand new thing, very important, simplifies everything. Of course we have operators, pretty standard, nothing new. And we maintain as few keywords as possible. 6 keywords and 9 semi-keywords. Finally, the first example of the language itself. Here's the data definition. The scheme above. Okay, this entity relation diagram above is equivalent to the definition below. So you can look at it and discover the simplicity of the language. How simple it is to write down this not very complicated yet containing 3 many-to-many relations database. Is very simple to write down. Well, you can imagine how simpler than SQL, much simpler. But the most important part, the three bottom lines, author, book, genre, and available, they are higher order relations, and they are defined by using the same language we define tables. So you can think about book and writer and genre as tables, and still they are represented uniformly with higher order relations. Very simple, surprisingly simple. I have no idea why nobody did it before. Domain and relation, these keywords. Why do we have 2 keywords for a relation? Basically, a domain is a relation, and relation is also a relation, but we maintain 2 keywords. Why? Domain is a special relation that contains all of its possible tuples. If you have a relation, a user defines what tuples belong to this relation. You can add and remove from this relation. A domain is a special case of a relation where you cannot add neither remove anything, because everything always belongs to it. It plays a role of a complex type, and it helps us to add structure to our tuples. It also connects to the idea of pragmatic typisation, because it represents ideas. It represents ideas of the domain knowledge with types. Here's the grammar of data definition. I took only 3 lines from the example above, from the previous example, to illustrate the grammar below. Yes, this is that simple. The data definition grammar contains of 7 lines. Pay attention to this symbol. Where is my mouse pointer? This symbol with 3 dots. I invented it in violation of BNF. It means a list of. So domains is a list of domain. It's just for brevity. So in order to define a relation, you say, I define a relation and provide a tuple that describes this relation, which is name and the list of domains. And the list of domains accepts basic types or relation names interchangeably. These two bottom lines, they are synonymous in linguistic terms. In terms of defining a language, these lines are synonymous, but I made them duplicate in order to highlight the fact that basic types are interchangeable with relation names. So types you define are interchangeable with types that are defined before you. That predefined types and user-defined types are completely interchangeable. Constructors.